Good morning, everyone. Welcome to EasyPower's webinar series, Arc Flash the Easy Way 2025. My name is Jim Chastain. I'm a solutions engineer with Bentley and the local EasyPower expert. Welcome to all. We've got a lot of material to cover today, so let's get started. I want to explain that we have this series broken into 4 parts. Today we're going to be covering the rules and regulations of the organizations that have responsibility for electrical safety. Next week we'll be doing the initial phases of an arc flash study, including modeling and data collection. The third week we'll be doing actually walking through the steps of an arc flash study. And then the fourth week, and these are all separated by 2 weeks, so I should re-up that. So the fourth week is going to be wrap up, labels, and mitigation. I'd like to start with a poll question and see kind of where the audience stands on this particular topic. No liability or obligation, but the first question is, where do you currently stand with respect to NFPA 70E compliance? Again, there's no obligation or liability. I'd just like to get some feedback on where people reside currently as we're getting into the topic this year. As we're waiting for the responses, everyone will receive a certificate of attendance, and that's why I encourage you to participate in the poll questions. Under the control box for the GoToWebinar frame, there is a handout section, and a copy of the slides are there, plus a couple other documents that we'll be touching on. Looks like we have about close to a quorum. Let's leave this open another 10 seconds. All right, thank you. So here how folks have weighed in. And it's pretty even distribution. Very frequently, beginners kind of come to us for an introduction to the topic, which is what this is all about, but we get it fairly deep into the technology. When we get into using the tools, I encourage everyone to follow along and stay with me. But feel free to ask questions using the question box in the control panel. Excellent. So the second question is, what area of this study presents the greatest challenge? And so that's precedes that you know something about what's going on. But this also focuses on what we're going to be including in the presentation and where we can amplify or make sure we're covering everybody's questions on a particular topic. Yeah, for those of you that are just getting started, I strongly recommend downloading the copy in the handout section of Practical Solution Guide for Arc Flash Calculations, because that is a soup to nuts explanation of the whole topic. So it looks like we got a quorum there. Let's see how people have responded. Pretty heavily on data collection. Good to know. It turns out that, yeah, I think data collection is probably one of the most misunderstood topics, and we'll get into that next week more so than we will this week. But thank you for participating. Now, I mentioned that this is available on the EasyPower website. We call it a new Arc Flash safety book. It's also in the handout section. It's free if you download it from the website or from this webinar. It costs $70 if you want to buy a hard copy from Amazon. So I encourage you at the very least, to download a soft copy and expose yourself to the details. I'd like to start with a case study that I've actually found in the accident report section of the OSHA website. It involved an electrician replacing some air filters as part of a routine preventive maintenance procedure on a bank of large forced air-cooled VFD cabinets that were supplied by a 2000 kVA 480 volt substation. He had replaced the first filter without an incident, and he heard a strange noise coming from another cabinet in the utility room. So he decided to investigate. Well, he did so by opening the door and poking his head in to see if he could locate the source of the sound. The first 2 or 3 cabinets that he opened, there wasn't a problem, but the last cabinet he opened produced a large explosion, knocked him off his feet, and unfortunately he died shortly thereafter. The sad thing, as sad as this event was, the electrician was not electrocuted. He died as a result of body-encompassing burns from an arcing fault. And it was initiated by the simple act of opening the cabinet door, which allowed a loosely connected phase cable to fall on the ground. And that's the intermittent contact was what was producing the buzzing sound that he was hearing. And it's because of events like this that the arc flash is our focus. And just as kind of a forewarning, as we get into more details on the safety requirements, see if you can pick out what was missed as far as the electrician training that could have prevented his death. Now, just a thought, my question is, did Ben Franklin discover arc flash mitigation back in the day? Well, he's the guy that's pretty much responsible or credited with defining lightning as a form of electricity, and he recognized that when air is a conductor, electricity can be dangerous. So he invented a lightning rod that redirected the electricity to ground. And the point I'm making is that's similar to what the current technology is, the most recent technology in facility protection, and that's arc quenching, which we'll get into in the mitigation discussions at the end of the series. So bottom line is lightning has been around, arc flash has been around. It's just only recently we've kind of discovered what it is. Since the days of Edison and Tesla, high energy explosive accidents occurred randomly in electrical systems, damaging equipment and injuring workers. The exact cause was not known, and some labeled the events as acts of God. Well, we credit Ralph Lee's work in the mid-1980s for putting a name to the situation, to the accident. He called it an arc flash event, and it defined it as a self-sustaining high current event where the current is going through a plasma arc, which is ionized air. The event releases large amounts of radiated energy, and it's not confined to the system hardware. I underline this because that was the major problem as far as defining the hazard, is that the system could be designed to deal with a fault, but not necessarily a fault that was outside the path of the system itself. So Lee's model estimates the amount of energy released over time and correlates the heat damage to unprotected skin. From time to time, I'm going to refer to the term bolted fault or available voltage fault current. And what that means, both literally and hypothetically, is the output of a connection point at a bus has a 0 ohm fault across all 3 phases. And in a breaker manufacturer, this is how they test a breaker to see if they can withstand a full phase bolted fault by placing a copper bar similar to this one across all 3 phases and then applying current to the top of the breaker. Well, in the IEEE data battery, the data testing that was done, the battery of tests generated an arc by initially having the current flow through a very thin wire, and all that current melted the wire, causing the arc to establish, and that's what permitted them to run the tests to characterize the nature of the arc itself. And it turns out if the arc is established, even a single phase to ground, if there's the plasma ball is large enough to touch electrified buses, that arc will propagate to other parts of the system. So during the testing, the definition of an arc really gives us a summary of these types of hazards that could be produced. There's usually a large amount of heat, in some cases in a worst case situation, greater than 35,000 degrees Fahrenheit, which exceeds the surface temperature of the sun. There's a potential for molten metal projectiles, potentially toxic gas from vaporized metal oxide or insulation that's been vaporized. There often is a pressure wave because of the expanding air due to the arc will cause the air to expand multiple times its volume, as well as the vaporization of the metal involved. Very often there's a loud sound boom. Frequently after being exposed to an arc flash, people report that their ears rang for hours, if not days after the event. And then frequently there's a very intense light, which could cause blurring and permanent eye damage. I put an asterisk by this last term, or the last line, and that's because whenever whenever we talk about PPE, the only real correlation we have to protection of humans is the measure of heat that is produced by the energy in the arc. And so if your system, as you grow to learn more about the nature and the energy involved in your system, you may want to consider PPE for other types of hazards or damage. I'd like to include one slide on the term arc blast. And second hazard that Ralph Lee described was called an arc, a pressure developed by arcs. Because not enough time has been spent to characterize the blast pressure itself, it still, I guess, doesn't receive its due, or it's not something we can quantify. So again, it's not presently covered by NFPA or IEEE 1584. There is a one paragraph note on it, and it basically contains the information I have here on the slide. Just a quick note on electrical injuries and hazards. Electrical fatalities, because of the understanding and awareness of arc flash, has been on a slight decline since the early 2000s, but in more recent years it's been ticking up, in part, we think, because of people taking things for granted. The thing to focus on, or the thing to be aware of, is a risk trade-off for electrical hazards. Even though there's a low frequency of events, in other words, less than 0.16% of the injuries due to electrical hazards involve lost time, there's a very high consequence of an event. In other words, even though it's the seventh leading cause of occupational fatality, its first or second listing as far as the most costly workers' comp. So it has far-reaching effects if someone gets hurt because of an arcing event or electrical hazard. There are several overlapping organizations that have an awareness or responsibility for electrical safety. At the top of the heap is the OSHA requirements, which basically fall under the general category of the general duty clause, and we'll touch on that briefly. Then, as in a category that's defined as consensus standards, there are documents or standards that apply to certain parts of the industry itself. And most of us are familiar with NFPA 70, which is the NEC document. And what we're going to be focusing on primarily is NFPA 70E and Z462, which are applicable for electrical safety in general industry. And these are regarded as consensus standards because technically they don't have any standing as far as legal documents, but they provide a methodology that companies can follow to meet the requirements or the suggestions in OSHA. And then finally, there's guides and methods to actually do the calculations. And we'll be focusing on IEEE 1584, although there's other methods, and part of the requirement is to document which methodology is being used for developing a safety program. I mentioned the general duty clause. Basically, it says employers must provide a place of employment which are free from recognized hazards. So much of this first hour is focused on making sure that everyone understands arc flash has been recognized as a safety hazard in the industry. Again, there's certain categories or articles in OSHA applying to personal protective equipment and electrical safety in certain areas of the industry. For instance, the generation and transmission and distribution market. But again, those are outside the purview for the most part of NFPA 70E. And with that said, I'll come back and show you that it still doesn't disregard the need for an arc flash study. OSHA in their CFR 29, section 1910 describes the connection between the OSHA requirements and the consensus standards. The relevant legislative history of the Act indicates congressional recognition of the American National Standards Institute and the National Fire Protection Association as a major source of national consensus standards. Again, the suggestion is employers following these standards meet the OSHA requirements. That's why even areas of the market, if you will, that are not required or covered by OSHA or NFPA 70E may select the path that they use NFPA 70E as their guide for electrical safety because they don't have to rewrite their own individual plan. We touched on NFPA 70, the National Electrical Code, because it covers construction, installation, and testing of equipment. And so for the longest time, it didn't really discuss arc flash hazards. In the more recent versions of NFPA 70, there's been this document, this article, saying that a arc flash is a hazard, and you should refer to NFPA 70E for details and guidance on determining PPE. The point to be made that I like to make is that this label image suffices to meet the requirements of NFPA 70. It doesn't meet the requirements of NFPA 70E. So someone taking delivery on a new piece of equipment that's recently installed should be aware that the labeling needs to be changed as soon as you turn the power on. A real quick look at the overview of NFPA 70E, basically three related chapters. We're going to be mostly involved with Chapter 1, which is the safety-related work practices. There's more and more emphasis on maintenance and special equipment going forward. I mentioned that the certain areas are not covered by the NFPA 70E, but many companies in these market segments still use EasyPower because they have adopted an internal policy of complying with 70E just to have to keep from reinventing the wheel. Just a real quick note on what you need to pay attention to NFPA 70E, and that is it gets updated every 3 years. And in the early days of, which back in the early 2000s, of NFPA 70E's inclusion of arc flash, there were a lot of changes with these updated cycles, which caused some companies grief trying to keep up with the changes involved. I will make a point. Yeah, so this series of webinars is not meant to be a book report on NFPA 70E. I strongly suggest if you're involved with electrical safety that you have access to your own copy of the most recent version of NFPA 70E, whether it's hard copy or soft copy, because there's a lot more to it than I can cover in a 1-hour presentation. And so then some of the updates have been more recent versions have been relatively small involved. One of the changes in 2021 was the inclusion or the update of the IEEE standard that's used to do the calculations. And then in 2024, there was some changes in definition and some special equipment included in Annex S. And again, I just want to reiterate, this isn't a book report on NFPA 70E. I encourage you to get your own copy and make sure that your needs are covered by stuff that I didn't include in this series. NFPA 70E is, as I mentioned, the electrical standard for electrical safety in the workplace. And these are all covered in different articles in the standard. The place we're going to be focusing on is the relationship between the employer and the employee. The employer must provide a safety-related work procedure and training. The employee needs to be able to follow those procedures and comply with the training, and especially when it comes to electrical safety and PPE conditions and maintenance. So nothing really new here. Now, these are my own words, but the prime directive of NFPA 70E is thou shalt not work on hot equipment. And as soon as we being a corporation or a company decides that's going to be our policy, then that means we understand and know how, our employees know how to put the equipment in electrically safe working condition. That is referred to as ESWC, and even when it's it's defined in NFPA 70E, even when it's company policy that you will not have electrical hot work, it doesn't eliminate the need for an arc flash assessment. And if you ask why, it's because PPE must be worn to test the equipment. The steps involved in establishing an electrically safe work condition are to de-energize the equipment, test the equipment, actually test it to make sure it's hot or not hot for starters, open the system connection, the breaker supplying the energy, test it again to make sure it's being de-energized, and during that process you must have on the proper PPE. So this requirement doesn't negate the need to do an arc flash study. Okay, this just repeats what I just said. The third part of the requirement is to have a mechanical notification process that prevents re-energization uh, based upon anybody that's involved with electrical work on the equipment. And so that's represented by the lock on the tag out. And if there's any locks on there, then I can't re-energize the equipment until they're cleared. All this is described in NFPA 70E, and the forms are stuff you can copy from the annex. Starting in Article 130, there's a description of electrical work that can and can't be done, and the requirements of doing the hazard assessment in the process. The two primarily risks that we're concerned with are electroshock and arc flash. And so they are covered in 130.4 and 130.5. So going back to NFPA 70E, when it says de-energized work is the only safe work condition, and that's their baseline. But then starting in 110.4, it talks about what's allowed for hot work if necessary. For starters, anything below 50 volts we're allowed to work on without being concerned about arc flash hazard or electrical safety. Then beyond that, electrical testing is permitted on de-energized equipment without de-energizing equipment if doing so produces additional hazards to employees in the area. And examples might be the interruption of life support equipment, deactivation of emergency alarm systems, or shutdown of hazardous location ventilation equipment. So when any of those are present, then hot work is permitted, and we jump into a different coverage as far as the safety factors. And then finally, the hot work on the equipment while it's still energized is permitted when the task to be undertaken is infeasible in a de-energized state. And what I mean by that is we have these basic standards or pillars that we need to verify before we can, and they apply to all parts of NFPA 70E, and that is the definition of normal operating conditions. The equipment must be properly installed per manufacturer's instructions. Equipment's properly maintained, used in accordance with manufacturer instructions. All the equipment covers are in place and secured, and there's no evidence of impending failure. Well, if one of those requirements for maintenance is to do an adjustment, diagnostic testing, or inspection of equipment while it's running, you can't very well do that when it's de-energized. So that's this last category of permitted hot work. And all of these hot work situations require a hot work permit. And that's article, well, it's included in NFPA 70E, and there's details of the description of the work, the justification for the work, the results of the hazard assessments. I think it's important to understand part of this form includes the need for management sign-off to ensure that the corporation or the company management understands that they're putting employees in an elevated hazard situation, and all steps should be taken for their safety. So this form, by the way, EasyPower can produce and include all the details and be updated as you need so. So that brings us to the risk assessments themselves. The first is shock risk assessment, and its purpose is to identify exposure, estimate the potential severity, and then determine if PPE is required. It's not related to arc flash or incident energy. It's only based upon the voltage of the exposed bus and it defines two boundaries. One's a limited approach boundary and the restricted approach boundary. And graphically, the limited approach boundary is the one farthest away from the equipment, and it's defined as the approach limit for an unqualified person unless that person's advised of possible hazards by a qualified person and is continuously escorted by a qualified person. It's important to note that neither of these hazards exist when the equipment's closed and secured and there's no exposure to electrified buses. And then the more close-in boundary is the restricted approach boundary, and it's the approach limit for a qualified person unless the qualified person is using PPE and other shock protective equipment, and the energized conductors are insulated for the qualified person. So again, these are based upon voltage, and they're fixed numbers, they're fixed boundaries based upon the voltage that's being exposed. Which brings us to the definition of an arc flash boundary. And in Article 100, the listing of the definitions, the arc flash boundary exists when an arc flash hazard exists, an approach limit from an arc source at which the incident energy is 1.2 calories per square centimeter is defined as the arc flash boundary. Now, these just aren't random numbers. The 1.2 calories per square centimeter has been determined to be the potential onset of second-degree burn on unprotected skin for 1 second. And that turns out to be a very low arc flash event that produces energy less than 1.2 calories. That happens. The point being, these are not, you can't just look at a piece of equipment and tell whether or not it's an arc flash hazard. And so, especially for people that have worked in the industry for a number of years, it's easy to take things for granted. And again, that's what all this education is about, is making sure that you don't take for granted your safety, because all you have to be right 100% of the time, in which case one bad situation where you're not right could ruin your day. So Article 130.5 is the detailed description of an arc flash risk assessment. And it covers everything up and including equipment labeling. So the purpose of an arc flash risk assessment is to estimate the likely occurrence and potential severity by considering the design of the electrical equipment and the operating conditions and the condition of maintenance. And so there's this table, 130.5C, that gives us some indication of the likelihood of a worst case event. Don't misread it to be a suggestion that you should wear or should not wear arc flash PPE. This actually goes more to the maintenance, considering what maintenance is and condition of the equipment is. And that's an area where things are evolving even as we speak. But wait, you might say, what if we've done our arc flash risk assessment and we're working in an older facility that has elevated incident energy behind the closed panel, and yet frequent circuit breaker operation means higher risk? What does that mean? Well, according to NFPA 70E, to operate a circuit breaker, we don't necessarily need to have PPE on us, as long as the equipment's been buttoned up and serviced properly. However, if we have any doubts about that, and there's some elevated hazard that we're aware of because of the study, the open and close procedure the company may describe may require an operator to stand to the side, not in front of the panel, and have PPE on the hand and arm, and then hearing protection in case of a worst case event on the breaker operations. So the point I like to make is when something like this is in place, it makes me believe that the company is serious about employee protection. In fact, the employees are aware of the hazards involved, especially on older equipment. Okay, so the arc flash risk assessments to determine the protective measures that may be required, what the arc flash boundary is, and what PPE should be used. And all of this should be documented in the arc flash risk assessment documentation, which includes the data that was collected, the trip times available in any protective devices, and then any elevated incident energy that requires mitigation if possible. Again, the more complete the documentation, the better it can be utilized by safety personnel and maintenance people working on the equipment. So we've defined the arc flash boundary. There's two acceptable methods to determine the arc flash boundary. One is the arc flash PPE and arc flash boundary lookup table, and the second is incident energy analysis. We're going to be focusing primarily on the second, but I'm going to touch bases on this table lookup stuff. In NFPA 70E, there is a table 130.C 7C that describes a listing of different types of equipment, in this case panel boards up through switchgear at different voltages. And if we know the maximum current and the clearing time, then they give us the arc flash boundary that should be respected on that particular when that particular bus is exposed. Now the caveat here, or the catch-22, is if I don't know what the max current is or the clearing time, how do I find it? Well, you find it by doing an instant energy analysis, and in which case you cannot use this table. Likewise, for PPE, we can also use the same table to determine what PPE is required. And again, the standard 1584, NFPA 70E gives us a description list of the equipment, the max current, the clearing time, the working distance, and then the PPE category. Again, I can't use this if I've done instant energy calculations, the instant energy method. And so that you might say, well, where do I use this or when do I use this? Primarily, it's available for people that haven't done an arc flash study, and for some reason they're having to do data collection with the equipment that can't be turned off, in which case you can assume a worst case arc flash PPE based on the definition of this table. Okay, so which gets us to the instant energy analysis method. So it's based on the working distance of the person. You're going to hear me refer to two different categories, two different distances. One is the working distance that's listed on the label, and the other is the working distance that's needed or stipulated for hot work. They're seldom the same number, and it's important to understand what that means to somebody walking by the panel and looking at a label. But the instant energy analysis method is fairly complex, requires extensive calculation. It's important to notice, and so the reason for it is it gives us a more quote unquote precise determination of PPE. I use quotes because in all the literature and all the standards and the test results that IEEE reported, they use the term estimated results because there's a lot of variability in the data that was taken during testing. It's important to notice that there's no specific method of instant energy mandated in NFPA 70E, but there's a list in Informative Annex D that talks about other methods, other scopes, and DC, which is not covered by IEEE 1584. Okay, once we've determined our incident energy and working distance, NFPA 70E directs us to this set of discussions. One is for an incident energy between 1.2 calories and 12 calories, and the other is for incident energy greater than 12 calories. And the caveat is that as long as our PPE is rated to equal to or greater than the estimated incident energy, then this description applies. The first category, which is less than 12 calories per square centimeter, requires long sleeve shirts and pants, arc-rated face shield and balaclava or hood, arc-rated outerwear, hard hat, safety glasses, and hearing protection. Greater than 12 calories has the same discussion, but for head protection, it requires an arc flash suit, hood, and the balaclava is no longer adequate. Now, this last line is, again, the soapbox that I kind of revert to, and that is, if you look at the fine print on labels or the discussion from PPE manufacturers, they talk about not being able to guarantee any level of protection. And in some cases, they say, well, it protects the wearer down to 1.2 calories per square centimeter. Well, if you recall, that 1.2 calories per square centimeter is the crossover point where there's a 50% probability of second degree burns. So I take that to mean even if I'm following all the rules and I'm wearing the right PPE, I still could get second degree burns in a worst case situation. I bring that up only because people don't necessarily take this discussion to heart. And I'm just reiterating the fact that arc flash is not a joking situation. I don't mean to be over dramatic. I guess I need to start EasyPower. The equipment that's likely to require examination, maintenance, or while it's energized requires equipment labeling. And hold on just a second. And to that point, each piece of equipment needs to have a warning label that includes the system voltage, the arc flash boundary, and at least one of the following: the incident energy and working distance, or the arc flash category but not both, the minimum rating of clothing or site-specific PPE. And so these two images on the right are minimal arc flash warning labels. Usually people want more than minimum required, and so the ability to put in customized arc flash labels is warranted. So give me just a second. I'm firing up EasyPower, and we're going to jump into an example that I call the arc flash paradox. And this is a conversation I had with an electrician in Oklahoma when I first joined EasyPower. He called up and said, "Jim, I've just purchased the EasyPower tools. I think I found a bug in the software." I said, "Well, let's connect online and walk through your one-line diagram." So as we did so, I walked through his system as he described it on the phone. He said, "First, you want to put a utility icon." So I'm using the EasyPower tools and the icon from the equipment palette on the left vertical sidebar, pick up a utility icon, place it on the one-line diagram. He said, "The next thing I have is a two-winding transformer." So again, I left click to pick it up, touch the pigtails, left click again. He said his incoming utility voltage was 12.8 kV. So I type in 12.8 and the tool connects the two and it knows what the voltage is on that bus. The electrician said, put a plain bus on the secondary of the transformer. So again, I pick up the plain bus, touch the pigtail. He said his distribution voltage was 480 volts. Everything's in kilovolts, so I type in 0.48. Now, as I move the cursor around the screen, you can see it changes the shape of the cursor. If I put the cursor over the middle of a bus, I get a quad arrow icon for my cursor. If I left click and drag, I can move that element anywhere I want to on the screen. If I hover over the end of a bus, I get a dual-ended arrow. I can left click and extend or contract the bus accordingly. He said extend this bus about half the width of the screen and drop a cable on each side. The cable is a circle with 3 inscribed circles on the equipment palette. I'm going to left click and pick it up, put the crosshairs on the bus, left click again, do the same thing on the other side. Now he said terminate each cable with a plain bus. So I'm going to reuse the icon. I'm going to pick up the plain bus, hold down control, and then I can put a bus on the end of the cable. Now you'll notice each one of these elements has double asterisk, which means my data dialog box is missing some minimum data. If I try to go to short circuit focus right now, if I click on this lightning bolt on the top center of the screen, the tool says, Jim, are you sure you know what you're doing? There's some equipment with incomplete data found. I can view the report, or I can go back to my one line and I can see those elements highlighted in red. The electrician had the responsibility of labeling the above ground distribution system for an oil field there in Oklahoma. He said, Jim, I've looked at the label on this first cable. I'm going to double click on the cable to open the dialog box. He said, this first cable is a single conductor per phase, so I'm looking at no per phase is 1. The type of cable is a 1C, which means each phase is insulated separately. The type of insulation was THWN because this was an outdoor run. So I need to scroll down a little bit and get THWN. And the size was 350 kcmil. So I'm going to pick out 350. The conductor was copper. The length was 50 feet. Now, because I've got auto calculate checked, as I'm putting these parameters in there, the tool is calculating my ampacity rating and my resistive and reactive impedance per 1,000 feet. So I'm going to click OK. He said, Jim, the second cable is the same as the first with a different length. So I'm going to right click on the first cable and copy, right click on the second cable and paste, and then open the dialog box. And sure enough, all that data came over. But instead of 50 feet, he said this cable was 1,000 feet long. So now I'm going to put 1,000 feet in there. Again, it hasn't changed my ampacity. And because these parameters are a ratio per 1,000 feet, I'm just taking a bigger chunk of that ratio. So I'm going to click OK. Everything that's needed for the transformer modeling is required, is on the nameplate of the transformer itself. Electrician said, Jim, I've looked at the nameplate on my transformer. It's an ANSI standard oil filled. So I pick out oil filled class OA, which means it didn't have forced air. The temperature rating was a fixed 65-degree rise. The connections was a delta with a Y grounded, the delta Y grounded. The rating on has a little red dot by it, which means it's mandatory data. The kVA rating on his nameplate was 1,000 kVA. We go to the impedance tab. I have more red dots. He said his Z impedance ratio was 5.75%. Now, nameplate may not have the X over R or the zero sequence ratio, but the tool will calculate those based upon industry standards. And when we go to the TCC plots, it's going to plot my damage curves automatically using those parameters. Now, the reason I like this example as much as I do is that he said he had only one protective device in his system, and it was a fuse in the electrical cutout switch. So I'm going to pick up the fuse switch and insert it in the utility feed into my transformer. And then I need to find characteristics for the data sheet. EasyPower has a device library with over 40,000 entries in it. And I want to make sure the data sheet for this fuse is included in my model. He said, Jim, I've opened up the utility cutout switch and looked at the label on the fuse. It's an AB chance fuse link. There's no fuse holder involved. It's just a piece of copper. So I'm going left to right and then top to bottom. He said the model was a Model T, and we both chuckled because of Model Ts in a different context came to mind. And he says the size is a size 12. Now, because I want to make sure it's connected to my device library, I go to the short circuit tab and I'm going to zero out my 15 and then auto calculate. The fact that 15 shows up, the tool's telling me, Jim, I found the part number you gave me. It's in the device library. The manufacturer tested it to an ANSI standard using symmetrical current, and the test fixture X over R was 15. The reason this is important, EasyPower is going to calculate the X over R for every bus in my system, and if anything has a protected device located in that bus, it will compensate for the difference between the test fixture and the installed element in my system. So now I'm ready to go to short circuit focus, and as I do so, I get a clean one-line diagram. Electrician said, okay, the first thing we want to do is look at a half cycle. I'm up here on the top row on the left. Half cycle, three-phase bolted fault. And we're going to fault all the buses with a lightning bolt on the far left. And as we do so, we're looking only at the A phase. We can look at A, B, and C phase, but because they're all the same, it's a bolted fault, they're going to have the same magnitude. So we'll just stay involved with our A phase to reduce the clutter. Said, okay, this makes sense. If I have a fault here on the secondary of the transformer, each phase will see 20,915 amps. If I walk 50 feet away to this panel, each phase will see 17,878. If I walk 1,000 feet to this panel, each phase will see 4,351 amps. He said that makes sense. Now I'm ready to look at my arc flash calculations. The arc flash icon is this little burning man symbol on the top row. Once I invoke that, now I get new numbers and new colors. And the electrician said, Jim, this is where I think there's a bug in your software. I said, I don't know what you're talking about. Explain. He says, well, right here on the secondary of the transformer, my arc flash boundary is 20 inches. My instant energy is 1.4 calories per square centimeter. So I know I can work safely on this bus with a 4-calorie PPE. If I walk 50 feet away to this bus, the arc flash boundary is 21 inches. My instant energy is 1.5 calories per square centimeter at a working distance of 18 inches. So I know I can work safely on this bus with a 4-calorie PPE. But if I walk 1,000 feet away, now my arc flash boundary has doubled, my instant energy has tripled, and you're telling me I need to put on more PPE to work on this bus hot. How can that be? I said, yeah, what are you talking about? He says, Jim, I've been an electrician for 25 years, and anybody that works with electricity knows the farther away you get from your energy source, the lower the energy is going to be. Your tool's telling me this energy goes up. How can that be? My response was, I've been an electrical engineer for 25 years, and I agree with you. I don't see how that energy can be increasing. Well, the reason for the story is to show the versatility of the tool, because at every point in your study, you're going to wonder, or at least want to know, how the calculations are being made. And to reflect that, you want to use this icon at the top center of the screen called Arc Flash, Arrange for Arc Flash. And as I do that, it shows me the calculations on the spreadsheet down below, and I can go through and look at each individual bus. if I look at the calculations for the secondary of the transformer, it's a 480 volt bus. The fuse is a protective device. We define the equipment as a panel with vertical electrode configuration, an electrode gap of 25 millimeters. We already knew the bolted fault current. The arc flash current, according to the model, is 14,018 amps. The branch current through the fuse is 526 amps. At that current, the fuse will blow in 64 milliseconds. Put all that into the IEEE equations, we get 1.4 calories per square centimeter at a working distance of 18 inches. We go to 50 feet away in this bus, it's still 480 volts, it's still the same fuse, it's still the same panel, electrode gap, but now our arcing fault current is 12,000 amps, and the trip time of the fuse is 82 milliseconds. And we put that into the IEEE equations, we get the arc flash boundary of 18 inches and a 1.2 calories per square centimeter. If we walk 1,000 feet away and look at this bus, it's still 480 volts, it's still the same fuse, it's still the same panel, but now my arcing current is 105 amps, and the trip time of the fuse is over 1.25 seconds. And so my instant energy is going to be considerably higher because the arc is going to last that much longer. In fact, if I select this bus, hold down Control and select this bus, and then fault the buses, both buses, I'll see that my trip time on bus 4 is over 20 times longer than it would have been on the secondary of the transformer. And so during that time, my 4-calorie PPE would not have been enough to protect me from that arcing energy. Well, I call this the arc flash paradox. And it describes the counterintuitive nature of arc flash. And what it really means is, in the same system, you can have low arcing current but high incident energy. It all depends on the time to clear the arc. So the takeaway that I want to make sure you're left with is you cannot just look at a piece of equipment and ascertain the arc flash hazards in the system. Okay, thank you for attending today. Pay attention to your newsletter for new announcements on arc flash and EasyPower. And be sure, if you want to play with the tools, you can access a demo copy of the software on the website. And join us in 2 weeks when we do Part 2, Data Collection and System Modeling. Thank you, everyone, and have a good day.